Hello engineers, and welcome to our video series on evolution from traditional VPN to EVPN. In this series, we'll take a close look at key evolution scenarios, such as moving from traditional VPWS to EVPN VPWS, from traditional VPLS to EVPN VPLS, and from traditional L3 VPN to EVPN L3 VPN. We'll walk you through the background and clear configuration and verification procedures to help you fully understand the evolution process and make your network configuration more efficient. In the IPv6 enhanced era, with the rapid growth of new services like 5G and cloud computing, traditional L2 VPNs such as VPWS and VPLS are struggling to keep up with user demands. Currently, these traditional L2 VPNs face three major challenges. First, the single active mode leads to low bandwidth utilization. Second, full mesh PW connections limit network scalability. Third, MAC learning in the forwarding plane slows down fault convergence. As a result, traditional L2 VPNs urgently need innovation and evolution. That's where EVPN, a next-generation VPN technology designed for all-service transport, comes in. Compared with traditional L2 VPN technologies, EVPN supports multi-homing access and traffic load balancing, making full and efficient use of network bandwidth resources. EVPN also enables automatic neighbor discovery, eliminating the need for full mesh connections. It unifies the control planes for L2 VPN and L3 VPN services by using BGP extensions to carry Layer 2 and Layer 3 reachability information. This separates the forwarding and control planes, simplifying network deployment and maintenance. On top of that, EVPN supports fault convergence within sub-seconds, facilitating path switching. EVPN offers a complete, mature service evolution solution for smooth, non-disruptive service upgrades, protecting customers' live network investments. Currently, the solution for evolving traditional VPN to EVPN supports two evolution schemes: integration and interworking. The integration scheme applies to scenarios where a large number of service nodes are deployed or the original VPN services are not hierarchically deployed. The core idea is as follows. First, deploy EVPN on a few key nodes so that EVPN and traditional VPN run in parallel to carry services on these nodes. Second, use EVPN to forward new services and traditional VPN to forward legacy services. Third, gradually deploy EVPN on other nodes. After EVPN covers all nodes and traffic switches to EVPN, delete traditional VPN. The interworking scheme applies to scenarios where original VPN services are deployed hierarchically. The core idea is as follows. First, upgrade the SPEs and NPEs to support EVPN. Other nodes still run traditional VPN. In this case, one service endpoint runs EVPN, and the other service endpoint runs traditional VPN. Second, the interworking function is configured on convergence nodes to enable interworking between EVPN and traditional VPN. Third, as the network and customer services evolve, gradually upgrade other nodes from traditional VPN to EVPN, eventually achieving full EVPN coverage. Let's take a look at a scenario with smooth evolution from traditional VPWS to EVPN VPWS over SRv6 using the integration scheme. Traditional VPWS, also known as Virtual Leased Line or VLL, is used to provide point-to-point L2 VPN services. Before the evolution, ACC1 is dual-homed to P3 and P4 over LDP or static PWs. Before the evolution, P3 serves as the active node, P4 serves as the standby node, and the PWs operate in independent PW redundancy mode. E-trunk master or backup protection is deployed between the PEs and CE, and no RR is involved. After the evolution, BGP VPN routes are advertised between the ACC and PEs through an RR. PEs are configured to work in single active redundancy mode based on ESIs, and EVPN VPWS services are carried over SRv6 tunnels. Seamless evolution to EVPN VPWS over SRv6 is then achieved. The overall evolution roadmap can be broken down as follows. Configure is ESv6, BGP EVPN peer relationships, and SRv6 tunnels. Configure EVPN and EVPL instances. Configure a delay for switching from traditional VPWS to EVPN. Bind an access side sub-interface to the EVPL instance. After all services evolve to EVPN, delete traditional VPWS configurations. Next, let's go through the detailed configuration steps. The NetEngine 8000 is used to demonstrate key points. First, configure is routes between ACC1, P3, P4, and the RR. First, enable IPv6 on ACC1's interface. Second, configure an IPv6 address for the interface. Third, enable is IPv6 on the interface and specify the ID of the is process to be associated with the interface. After the configuration is complete, is establishes neighbor relationships and floods link state PDUs, or LSPs, through this interface. Is IPv6 also needs to be configured on ACC1's loopback interface for the establishment of BGP EVPN peer relationships later. The configuration process is similar to the preceding one. The following uses ACC1 as an example to describe how to configure is IPv6. The configurations of the RR, P3, and P4 are similar to that of ACC1. Next, let's check the is configuration. Run the display is peer command to check is neighbor information. If the state field is up, ACC1 has established an is neighbor relationship. Run the display is route command to check ACC1's is route information, including the outbound interface, next hop address, and link cost. The command output shows that ACC1 has learned the routes to the loopback interfaces, network segments, and locator of the RR, P3, and P4. Next, we will configure BGP EVPN peers. The RR is used to establish BGP connections with other routers to reflect BGP routes. Its basic configuration is as follows. The following uses ACC1 and the RR as an example to describe how to configure BGP VPN peer relationships. The configurations of P3 and P4 are similar to those of ACC1 and the RR. Then, configure an SRv6 tunnel. First, enable segment routing in the IPv6 forwarding plane and enter the SRv6 view. Second, configure a source address for IPv6 packet encapsulation. Using the IPv6 address of a loopback interface is recommended. Third, configure an SRv6 locator. Fourth, enable is SRv6 to advertise locator routes. Fifth, configure the device to send EVPN routes with the SRv6 encapsulation attribute to a specified peer. The following uses ACC1 as an example to describe how to configure an SRv6 tunnel. The standalone RR does not require SRv6 related configurations. The configurations of P3 and P4 are similar to that of ACC1. Run the display segment routing IPv6 local SID end DX2 forwarding command to check information about the SRv6 BE local SID table. The command output shows that the SID belongs to the configured SRv6 locator address pool, indicating that the configuration is correct. In this case, the service type is n.dx2, indicating the EVPN VPWS service scenario. Next, let's configure EVPN and EVPL instances. The basic steps are as follows. The following uses ACC1 as an example to describe how to configure EVPN and EVPL instances. The configurations of P3 and P4 are similar to ACC1. Estimate the delay based on the service volume on the live network. The delay measurement starts after newly added EVPN VPWS instances on all devices go up. The configurations of P3 and P4 are similar to that of ACC1. Next, bind the EVPL instance to the corresponding AC subinterface on each device. Enter the view of the AC subinterface bound to the traditional VPWS service. Then bind the subinterface to the EVPL instance. The following uses ACC1 as an example to describe how to bind an AC subinterface to an EVPL instance. The configurations of P3 and P4 are similar to that of ACC1. After delayed switching from traditional VPWS to EVPN is configured, you can check the service forwarding status on the interfaces of ACC1, P3, and P4. The command output shows that the currently effective service type is EVPN VPWS, indicating that the device has completed service evolution. The following uses ACC1 as an example to describe how to check the service type that takes effect currently. The configurations of P3 and P4 are similar to that of ACC1. Run the display BGP VPN EVPL instance id command on ACC1 to check EVPL instance details, including 1. Local status information on ACC1. The EVPL instance status is up on both the main interface and sub-interface, indicating that the local EVPL instance and service interface have been activated and can forward packets. 2. Remote information RR, P3, and P4 information can be found. 3. DF election information. P3 and P4 are the primary and backup DFS, respectively, and their ESIs are the same. 4. Tunnel type information. The EVPL instance has successfully recurs to an SRv6B tunnel. Run the display BGP EVPN all routing table command on ACC1. The command output shows EVPN routes sent from the remote ends. In this example, the command output shows that 5 Ethernet AD routes exist in the EVPN instance named EVRF1. Run the display BGP EVPN all routing table add route command on ACC1. The command output shows details about EVPN routes sent from remote ends. If services do not meet expectations after being switched to EVPN, run the following commands to roll back them to traditional VPWS. After the rollback, run the related command to check whether the service type that takes effect on the interface is traditional VPWS. If it is traditional VPWS, the rollback is successful. Run the display MPLSL2VC command on ACC1 to check traditional VPWS connection information. The command output shows that ACC1 has established connections with P3 and P4 and the connections are in the up state, indicating that the traditional VPWS service is normal. Here, ACC1 is used as an example. The configurations of P3 and P4 are similar to that of ACC1. After all services are evolved to EVPN, you need to delete traditional VPWS configurations. First, restore the PW redundancy to FRR so that the active or standby status is determined locally. Delete traditional VPWS connections, including the primary and secondary PWs. Run the display BGP EVPN EVPL instance id command on ACC1 again. The command output shows that all statuses are up, indicating that EVPN services are normal. Run the ping EVPN VPWS command on ACC1 to check EVPN VPWS network connectivity. The command output shows that the connectivity is normal, no packet is lost during forwarding, and EVPN services are normal. At this point, the evolution from traditional VPWS to EVPN VPWS over SRv6 using the integration scheme is complete, and all services have been switched from traditional VPWS to EVPN VPWS. That's all for this issue of configuring evolution from traditional VPWS to EVPN VPWS over SRv6. Thank you for watching, and see you next time.